Okay, I think we should start. And if you recall, we were working on an example, but I told you that there was a second part to the problem that I didn't have time to do it, so I'm going to do it today. If you recall, just 2 days ago, the example was one in which we're given a stream function. We're told that this is a stream function for a flow. And the first part of the problem was to obtain and draw the streamlines that go through the origin. And we talked a little bit about this. For example, we said just by inspection of the stream function, we know that we're dealing with a steady flow because there is no time dependence there. And we also know that it's a two-dimensional flow because only x and y enter. And remember, the concept of the stream function only comes about in the two-dimensional case. All right, so the problem was then to knowing that to find the stream functions that go through the origin, we first find the value of the stream function at the origin, and that happened to be 0. And then going back and substituting 0 for the value of the stream function, then we get an equation that we solve and gives us the equation for the streamlines. And remember, there were two cases. When we set that equal to 0, we ended up with these two factors. So the two options that we had was to set y equal to 0. That would satisfy the equation, and that gives us the x-axis. So that it's this streamline, horizontal one. But then the other option is to set the quantity in parentheses to 0. And that gives us a pair of straight lines, the lines defined by the equation y equals plus or minus square root of 3x. And those are these two, this one and this one. So one has a positive slope of square root of 3, which is this one. And the other one has a negative slope of minus square root of 3, and that's that one. So there are those. You might say that these are three streamlines that go through the origin. The second part of the problem is, again, knowing that we have that stream function. Let me get a white piece of paper. The same stream function, but now we are asked to find the flow rate through this plane. So we call it the plane AB. So what we're doing is we're taking the coordinate system, x and y, and we're drawing a plane, which of course in the two-dimensional representation is just a line, but it represents a plane when you're thinking about the direction into the bore, the width of the flow. So this is a plane that we call the plane AB. We want to know what is the flow rate that is crossing that plane. You know, how much fluid, volume flow rate, is crossing that plane. And you recall, you might recall from last time that the way we find the flow rate, for example, if we have say I have here 3 streamlines, and I know the value of the stream function on each of those lines, what is the flow rate, for example, between the top streamline and the middle streamline? What is the flow rate? Say that again?
D psi.
And what is D psi?
The flow rate between...
No, but what is D psi? There's no D psi in the figure. You really want to say delta psi, but it is the difference between the values of the stream function. So the D psi that you're talking about is really delta psi. And it would be, for example, if I'm asking for the flow rate between the top and the middle one, it will just be psi 1 minus psi 2. The difference between those two numbers would give you the flow rate. So how do I find then the flow rate that crosses this plane between A and B? How do I find that? Which value?
0, 1, and
Where? Into the stream function. So essentially, find the value of the stream function at those 2 points, at the 2 points that intersect the axis. Right? So find the value of the stream function here, find the value of the stream function there. Even without knowing the shape of the streamline that goes through those 2 points, we don't really need to. There is a streamline that goes through there, one or more, and another one that goes through there. And I don't really need to know the shape of them. If I know the value of the stream function at A and B, and then I subtract them, then I know how much fluid is crossing that plane from A to B. So we say, well, that we set out to find those 2 values, the value of psi at A, the value of psi at B. Just plug in the coordinates, like he said, the value of x, the value of y, in the function that you see there above. So x, for point A, x is equal to 1, y is equal to 0. You plug it in and you find 0. And then you do it again for B. You plug the value, the coordinates for the point B are x equals 0, y equals 1. You plug them in, you get that psi at B is minus 1. Now, are we surprised to see that psi at A is 0? Remember part A of the problem was to find the streamlines that go through the origin? And where was the value of the streamline at 0? In part A, it was 0. So how come at A the streamline value, the stream function value is 0? It is the same streamline, right? It was that streamline, the horizontal one, that went through the origin. Also, of course, goes through one of the points, one of the ends of our plane. So, of course, that has to be 0. The other one is new because we never calculated the value of the stream function at a point such as 1, and the streamlines that we drew that corresponded to psi equals 0, there is no vertical streamline. Right? There is the horizontal one and the 2 straight lines at an angle. All right, so the answer to the question is simply take psi at B, subtract it from psi at A, and you get minus 1, and that is the flow rate. The units, of course, would be whatever units you're dealing with. You will always get a flow rate per unit depth. So the flow rate, for example, in SI units would be cubic meters per second. But since you're doing it per unit depth, so it's cubic meters per second per meter of depth, the units are always going to come out to be meters squared per second, but it's really because it's cubic meters per second per meter of depth. But that's it. That's the answer to part B. And we don't have any idea what the streamlines look like. But if you were to go ahead and actually plot all of the streamlines, that would take a little bit more time. You can do it, nowadays you can do it very easily, but if you do that, remember we only sketched the 3, which I lost. We only sketched those 3. But suppose that we're asked to fill it in, draw all of the streamlines, then you actually would get something that looks like that for that stream function. That would be a schematic of several streamlines. I drew them in blue this time, even though I drew the original ones in red. Let's put this like this. So at the bottom you have the ones that we calculated first, and then at the top you have the entire field. And I also drew our plane. Our plane AB is right there. And what we found was how much fluid was crossing that plane, that line that goes from A to B. You can see that, of course, these 3 straight lines are here. Now they're blue, but they're here. Of course, one is the horizontal blue line, and the 2 straight blue lines here, this one and this one, are still there. But I added more. And you can see, for example, what the flow field looks like, what the streamlines look like. And they could be going one way or the other way. So, for example, let's say if the flow is coming down this way, maybe the direction of this would be like that, right, as it comes down. And then what we're seeing that is happening here is that this one is turning, like that. This one is turning like that. Right? And this one is turning that way. And then I already know how much is crossing this. Despite this complicated flow field, I already know how much fluid is crossing that plane. So that's part of the usefulness of dealing with a stream function. We'll do more. Does anybody have a question? Yes?
What happens to the center streamline if you cross it down with the origin?
Yeah, well, it doesn't really cross. So there are several ways in which this could be interpreted. So for example, this one, all right, it really depends on more particulars of the flow field that we're not talking about. But you could, for example, interpret this to be a stagnation line. So it comes here and maybe it comes to a stagnation point here. So this is a stagnation point. And then, of course, you know, if you get very close to that line, I guess I could try to draw it here. You know, I get very close. I'll draw it in this color. So I'm coming this way. That's going to turn, right, that way. If I am very close but not quite there. But then if I happen to be on the straight one, then that goes to a stagnation point there where the fluid would stop. There are many things that can be done with this. For example, this could represent the flow in a corner. So if you just say, let me ignore most of this flow field and just pretend that this is a solid wall and that this is a solid wall. So I just have a corner. Maybe I'll draw it again. So suppose that I say, ignore everything except that line that you were talking about and then this one. The rest I don't care what it is. So then what I have here is a flow field that represents some fluid that is rounding this corner and going that way. Okay? And I could say, well, this could be a wall. I'd say this is a wall. All right? And so this whole streamline simply is some flow that is coming this way, encounters this corner, and it has to make a turn. Okay? There are many other features that we would need to discuss. For example, if this is a wall and there is viscosity, then there has to be a no-slip condition there. But we'll talk about that later when we start talking about the difference between potential flows and rotational flows or viscous flows. All right. Any other questions? Yes?
So we calculated the flow rate to be -1. How do we know which direction that means?
That's a good question. It could be either. We wouldn't know exactly unless we know which direction the flow is going. So we would need to have more information because I could very well reverse all of these arrows that I wrote here and have the flow go the other way. Right? We just know that there is one crossing one way or the other depending on the direction of the flow.
Is there no significance to the negative sign?
Not unless you establish, which direction is positive and which direction is negative. All right. Any other questions? Okay, so the next item will be so we tackled conservation of mass, and the stream function, remember, was defined for a two-dimensional flow so that it would satisfy conservation of mass. So we've done enough with conservation of mass. The next thing we would do is conservation of momentum, or Newton's second law. But this is a good point to break, and I do want to ask you some questions using the clicker. We haven't done that in a while. So I'm going to ask you some questions pertaining to not the previous lecture, but 2 lectures ago. So when we were talking about the first part of chapter 6. Okay, so if you're looking in your notes, go 2 lectures ago. And here's the first question. Although we also talked a little bit about this 1 lecture ago. The divergence of velocity Is it a scalar quantity, a vector quantity, a second rank tensor, or none of the above? Okay. I'm going to close it. All right. So 165 of you here with your eye clickers. Very good. It is a scalar quantity, right? The divergence of velocity. Velocity is a vector. Velocity is a vector. But when you take the divergence, what you get is a scalar. In fact, it has a physical meaning for us. I'm not sure if I have that question. I may have that question. Let's see. No, this is just, we'll talk about that one later. So, give you these two quantities, partial u, partial y, partial v, partial x. What do they represent? Linear strain rates, rotation rates, accelerations, or none of the above? All right. Okay, waiting for 3 people, 2 people. That should be it. Okay, so linear strain rates, rotation rates, accelerations, or none of the above? The correct answer is B. They represent rotations. All right. So for those who know that they are rotation, how do you know that they are not linear strain rates? Somebody who knew the right answer. You get the right answer?
Is that because they could do the streamline?
No. Wrong answer? Right answer, wrong answer?
I said A.
Huh?
I said A.
You said A. What did you say? A. Who said B? Okay. Why? Why? How do you know that they are not linear strain rates?
Oh, I just recognized it as the curl.
Well, it's part of the curl. Okay, that's good. They are not the curl, but they are in the curl. And those two happen to be in one component of the curl.
Well, is it because you have both directions changing, so it's like twisting like that?
Yeah, that's the best. I mean, that's good too, but that's it. The way you recognize linear strain, which is stretching or shrinking, it has to be the partial of the velocity in its own direction. So if I'm looking at u, it has to be u in x, right? Or v in y. That can stretch, or w in z. But if it's the variation of u with y, right? Then it's I'm looking at u here and u here in y. So u is here, here is here. And they're different. So then it'll make it rotate. Okay? So is the fact that they are crossed, they are not in their own direction. They have nothing to do with accelerations. That's just to fill in the space. And none of the above because also fill in. All right. So I really would expect that you would be hesitating between A and B only, right? Okay. If anybody has a question, just raise your hand. Okay. If the vorticity is 0, the fluid elements A do not accelerate, B do not deform, C do not rotate, D none of the above. If the vorticity is 0. Got it? Did you answer? You guys still waiting? 58, 60, 3 more, 2 more. Oh, it's a new one. 2 new one, 3. People just walk up. Okay. Correct. The vorticity is 0. The fluid elements do not rotate. Because vorticity is directly related to the angular velocity of the fluid element. They could deform. A fluid element can deform without rotating. Because as long as that bisecting line of the original angle remains in the same position. So if this is the corner of the element that I'm looking at, and here is that bisecting line, this line bisects this angle, this could deform, but I don't rotate this line, as long as it remains. So what we're looking is actually for rotation. So and so the connection then, I told you vorticity is related to angular velocity, but what is exactly that relationship between vorticity and angular velocity? Is vorticity the angular velocity? Is it half of the angular velocity? Or is it twice of the angular velocity? Or none of that? And I think most people are very fast on this one, so I'm going to close it quickly. You just finish. What happened to the other two? There they are. Okay, so hopefully because you answer very fast, you got it right. Yes. So it is twice. Vorticity is defined as twice the angular velocity. Remember, I told you that one way to think about it, the angular velocity has a 1/2. I would say if we just multiply times 2, we get rid of the half. And so that's one way to remember that vorticity is twice the angular velocity. And this is actually related to, I just gave you an explanation of this. So this one, everybody has to get it right. Because I just explained it, right? A fluid element can deform without rotating. True or false? All right. And then we'll see if everybody's really paying attention. 3 more. One still thinking. All right. I only expect perfection, but there is no perfection, right? There is never perfection, right? So 15 people weren't paying attention when I was explaining it right here. Deforming, no rotation. So a fluid element can deform without rotating. The answer is true. Okay, enough of that. Okay, so now we're going to talk about Newton's second law. And pay attention, it's, I'm sure you'll find it somewhat mathematical, but it's important for you to know where things come from. So first, let's step back for a moment. Why does that look so bad? Is that clear now? So go back for a moment to many, many lectures ago when we were looking at Newton's second law, but when we were ignoring any of the shear forces, in fact, any of the viscous forces. So this equation should be in your, somehow in your memory banks. It's our Newton's second law. The first term, negative gradient of pressure, is the forces due to the pressure field per unit volume. The equation is per unit volume. the weight of the fluid element, of course, per unit volume, and the rho A, the MA term in Newton's second law, but divided by the volume. And I just put here in little, even though we know what the acceleration means, right? Acceleration has those components, the local and the convective acceleration. And that was our element that we were looking at when we derived this equation. This goes back to the second week, maybe even the first week. So that's my element. There are the pressure forces. By definition, the pressure forces are perpendicular to the surface and point into the surface. So for those three sides, those are the pressures. And then you can see also the weight there. So those are all my forces. That's, of course, when we left viscous forces out. So suppose that I say that I want to include now the shear stresses that I left out. So I go back and say, well, let me revisit this. I mean, this is just for the purpose of notation. I'm going to include all surface stresses, not just the pressure, but anything else that might be acting on the fluid. I'm going to use these two symbols. Sigma will represent normal stresses perpendicular to the face of the element. Remember, we used sigma a long time ago for surface tension, so do not confuse it. This sigma is not surface tension, it's a stress. It's a normal stress. And then tau, the traditional symbol for a shear stress, a stress that is tangential to the surface. So then I redraw my fluid element right there. I put a certain orientation to my coordinates, x, y, and z. And now I didn't put the weight, so I wouldn't clutter like I did in the original figure, but only the surface stresses. And I drew them in different colors, so we distinguish them at this point. So the normal stresses, the ones that I call sigma, are perpendicular to the face. Notice that they are pointing out. So don't think of them as just being pressure. There could be more. We know pressure points the other way, but this sigma points out. And then the shear stresses. And of course, on any face, the shear stress could point in any direction, so I have to really write it in terms of two components. So on this face, which is perpendicular to the y-axis, I have a shear stress pointing up and another shear stress pointing in the x direction. So that completes all of the stresses on these three faces. And of course, I would have equivalent stresses on the three hidden faces, the ones that we don't see in this. So now what I realized is that I have to have two subscripts to organize my stresses so that I can recognize them. So I say I'm going to use two subscripts for both, for sigma and for tau. Each one of these sigmas and each one of these taus will have two subscripts to identify them. And in the case of sigma, it's just I and I. It will be a repeated subscript, but in the case of tau, it'll be I and j. So the first subscript will tell me which face the stress is acting on. First subscript. The second subscript will tell me which direction the stress is acting in, what direction it points at. So let me see if you get that. For example, if I want to put the two subscripts to this sigma right here, what are the two subscripts that I use? YY. You could say JJ if you are using I, J, and K for the directions. But let's just not bring more complication. Let's just use X, Y, and Z. So YY. The second Y should be clear because the second Y tells me the direction, and this sigma is pointing in the Y direction. So the first one is also Y. Why is that? Huh? Because the label that you use for the face of the element is the label of the axis that is perpendicular to it. All right? So therefore, this face is a Y face because it's perpendicular to the Y-axis. The face here in front, which face is that? That's an x phase. So for example, this tau here that is pointing up, which tau is that? Tau x z. Right? So that's the idea of the two subscripts. So if I do this, then I could put all of my stresses in a 3x3 matrix. All right? So I could put them all like that. Let me put this here. All right. I'm calling them all tau here. I'll tell you in a moment. Remember the sigma, the one that is perpendicular to the face, has the pressure in it. That's why it has a different symbol instead of tau. So it has the pressure and something else. So you don't see that here because I have separated the pressure out. Suppose I separate the pressure out. I'll tell you later how we do it. Then I can I can organize all of my stresses in a 3x3 matrix. We call that a second rank tensor. You may have seen that as one of the answers for one of the questions. And you probably said, what the heck is that? A second rank tensor, because we hadn't talked about it. Well, because this is a second rank tensor. It's essentially a 3x3 matrix. It's just a fancy name for a 3x3 matrix. So that's a second rank tensor, and it has all of those stresses. Remember, the pressure has been filtered out. One important feature of this matrix, and we're not going to prove why this is the case, is that it is symmetric. So it is symmetric. That means that the tau xy, for example, this tau xy, is equal to this tau yx. Right? Remember, the tau xy is acting on the x phase in the y direction. The tau yx is acting on the y phase, but in the x direction. But they happen to be equal because this matrix is symmetric. And that's easily indicated by saying that, tau xy. If you flip the subscripts, the value of the stress is the same. All right, so now let's do the following. With that stress field, how could I find the force that is acting on my element? Okay? Suppose with that distribution of stresses on the surface of the element, can I determine the forces? Of course, the forces would be something like the stresses times the area, right, on which it is acting. But you have to, the force is a vector, so there is a component of the force in x, another in y, another in z. And we have to separate them out. So let's say, for the sake of this argument, that we're going to find all of the forces that act in the x direction. So then you say, well, what is acting in the x direction? Certainly this sigma is acting in the x direction, but so is this tau, and this tau on top, right? They're all in the x direction. And of course, the ones that are on the hidden faces that have direction of x. So I say, okay, let me carefully look into that. So here is, say, the x direction. And those are the three that I just pointed out in the other figure. Maybe I'll keep this 3D figure here. So I'm just taking the x direction. So I'm taking this sigma right here, which is this sigma xx. I'm taking this tau that I told you, which is tau yx, and this drawing it appears on top. And then this one that was on top here, which is a tau zx, is actually now here. I'm reorienting the face so I have x in the positive direction. So I have those three and the other three that I don't see. Right? Well, I do see the sigma xx in the opposite direction. That would be right here, but I didn't want to draw it. Right? The sigma xx on the back side. And so I don't have those corresponding stresses on the other faces. So now let's say, how do we find the force? Well, I didn't want to go through the entire derivation again because it's tedious. And we have already done a similar derivation when we did the pressure. So if I go through that derivation, which if you recall when we did it for the pressure, it meant that we would use a Taylor series. So we would have the value of the stress at the center of the element, do a Taylor series expansion to the right, a Taylor series expansion to the left, then take the other stress, do a Taylor series expansion from the top and bottom, and so on. So if you do all of that, which again would be not too different from what we already did, you would find the following. That the force per unit volume, that's important. Remember, in our Newton's second law, we always write everything, that's dead, per unit volume. So the total force per unit volume involving all of these stresses would be that. Partial of the sigma xx with respect to x plus partial of the tau yx with respect to y plus partial of the tau zx with respect to z. All right? But remember, I told you that the stress matrix is symmetric. So I can flip this just because it's more convenient. So all I'm doing is flipping this y and this x here. So I'm writing xy on this term. And I'm flipping this zx and writing it xz. So I can have all the x's first. So sigma x, x, tau x, y, tau x, z. Well, that's the force per unit volume due to these surface stresses in the x direction. And then, of course, you realize I have to do the same thing in the y direction and the same thing in the z direction. But we're not going to do that because you get an equivalent expression. When you build it all, when you put the one in the x direction, the one in the y direction, and then the one in the z direction, you put all of them together, you get this that you see at the bottom. The mathematics here are a little bit above your grade. So I'm not going to be too extensive on this. But this is what you get. Remember that I told you that we were separating the pressure, right? When I wrote the matrix, it only had the taus, and I told you it's because I was separating the pressure out. Well, this is exactly what I meant. The sigma has the pressure part, which is this first term. You can see the minus sign because we pointed sigma out of the face, and we know pressure is into the face. So that's why there is a minus sign. And then the other part only has the so-called viscous stresses, the tau. So don't worry too much about it. Just understand a little bit what the explanation is. This is a divergence. Like we've seen, we're taking the divergence to the velocity, but now we're taking the divergence of this second rank tensor. That's a little bit more complicated. Do you know what this I is? That's the identity matrix. Right? So this is the identity matrix. So this is just a matrix that has 3 ones in the diagonal, and then the rest are zeros. Why is that? In connection with the pressure. Because the pressure only acts in the normal direction. There is no pressure tangential to a surface. The pressure is only normal to the surface. That's why the pressure was only a component of the sigmas, but not of the taus. So that's it. That's the missing part, is this term. So when I go back and take, well, what was my original equation right there, right? This was Newton's second law without the shear stresses, the viscous stresses, rather. When I put them back in, I get this new term. This is the new term right here. So all that long story, I could have told you, this is the equation. And these are the terms that we're missing. But I don't like doing that. I want you to at least, some of you will understand where it came from. So that's the new term. Everything else we already knew. Pressure forces per unit volume, the weight per unit volume, the MAE per unit volume. This is the new one. And those are the forces. So when you can label them, of course, you'll first one, pressure forces per volume. Second one, the weight per unit volume. And now the new term, the viscous forces per unit volume. That's a very general equation for the motion and deformation of a substance that moves and deforms. We're learning fluid mechanics for the first time. So the substances that we are going to be looking at are the same ones that you have been looking at this point. Water and perhaps air. Which happen to be which type of fluids? Water and air. They are Newtonian fluids. So when the fluid is Newtonian, do you remember the expression for tau for a Newtonian fluid when we did the very simple shear experiment? If I do the shear experiment where I move one plate, fix the other plate, and then this fluid moves like that, right? What was our expression for tau, the shear stress? Mu du dy. Which tau is this, by the way? With the subscripts. We only call it tau because that was the only tau. But if I want to label properly this tau, which tau is it? You need coordinates, right? X, Y. It's really tau yx, but because it's symmetric, it's the same as tau xy. Right? So now we can actually be more proper and put it right there. And that's because in that problem, that was the only tau. But in a very complex problem, there are all of these taus. Right? So, but this was for a Newtonian fluid. So you can see how the tau for a Newtonian fluid is related to the, what do we call this, the u dy? The strain rates. Right? The stresses are related to the strain rates through the viscosity. So the only thing that is pending for us to have a complete picture is to say what, oops, this is for a Newtonian fluid. And it's actually nice and easy. It's right there. This term that I underline here with the two purple bars, the viscous force per unit volume for a Newtonian fluid, happens to be this. There is the mu that we were talking about, but now a new, well, not a new operator, but a new for this class. What operator is that? This operator. No, it's not called the second gradient. It's the Laplacian. It's the one that was missing from before because we didn't need it yet. That's the Laplacian. Should be an old friend of yours from calculus, from vector calculus, but now it shows up here and it's very important. It's the Laplacian. What type of derivatives appear in the Laplacian? Second derivatives. Right? So if, how come, if tau, where did I do the tau here, is related to the velocity, is directly proportional to the first derivative, why are the second derivatives showing up here? That's a little harder question. These are second derivatives. Here's the mu. If tau is related to the first derivatives of velocity, the strain rates, through mu, second derivatives here, why? Because what's in the divergence of tau? Derivatives of tau. You would have to go back to when I said the total force, well, this term. The divergence of sigma was when we put together all of the forces, but the forces are proportional, are related to the derivatives of the stresses at the very top. So it's because of that. It's like you're differentiating one more time. So, long story, to arrive at our equation. When you put it in there, our momentum equation becomes that. Note that I'm saying this is for a Newtonian fluid that has constant density and constant viscosity. But that's all we really need to learn at this point in our study of fluid mechanics. Constant density, constant viscosity. And here is our equation. The all terms are the same. Pressure forces, weight, the new term for the viscous forces, and the acceleration. This is a very famous equation in fluid mechanics, and it has a name. Even though it's just Newton's second law, even though we also refer to it as the momentum equation. Does anybody know the name? That's the one. The Navier-Stokes equation. So that's the Navier-Stokes equation. If anybody ever asks you what the Navier-Stokes equation is, you have to know that it's really an expression for Newton's second law for a Newtonian fluid. Most commonly referred to as the momentum equation for a fluid. The momentum equation for a fluid. There is a much more complicated version of the Navier-Stokes equation if the density is not constant and the viscosity is not constant. It has a lot more things in it. It gets more complicated. That's all you need to know. This version of it for Newtonian fluids, constant density, constant viscosity. Does anybody have a question? Yes?
Could you go over the questions again?
Oh, so what's the Laplacian? Since it's not in our original review, what is the Laplacian something? Of course, the something that we care about is the velocity in Cartesian coordinates. Nobody knows? Second derivative of the velocity. Second derivative of the velocity. Second derivative of the velocity. So it's the sum of the second derivatives of the function with respect to x, y, and z. But it's the second derivative. That's the Laplacian in Cartesian coordinates. And it's missing from your table of operators. I didn't want to give it to you at that time yet. But any other questions?
Is it a scalar quantity or?
Good question. What is this? Velocity is a vector. What is the Laplacian of a vector? Huh? What is the Laplacian of a vector? If it is a scalar, this is a scalar. What is this? You're going to have an equation that has one term a vector and another term a scalar adding together. It is a vector. So the operator doesn't change the type of quantity. Velocity is a vector. The Laplacian operator of velocity is also a vector. You have a good long weekend, and I'll see you on Wednesday of next week.